Hello, this is an A-level maths video. It's a pure mathematics year 2 video based on section 1.1 of the textbook, which is all to do with proof by contradiction. So here's a question for you to start thinking about right away. This is going to introduce us to this topic. Explain why a triangle cannot have more than one obtuse internal angle. Of course, I'm sure you remember, but an obtuse angle is an angle which is between 90 degrees and 180 degrees. Pause the video, make sure you think about it, and only restart once you think you've got an answer. Okay, did you get anywhere with this? Well, here's one of the things you could have said here. You could have started off by saying, well, each obtuse angle in our triangle is going to be greater than 90 degrees. So if there is more than one of those, so two or more obtuse angles are going to add up to more than 180 degrees. And of course, that's impossible, isn't it? Because we know all angles in any triangle must add up to exactly 180 degrees. So therefore, our conclusion must be that a triangle cannot have more than one obtuse internal angle. Did you get something similar? Well, let's just have a look at the logic behind our argument here, which you may have come up with yourself. I'm just trying to move the paper so that we can see it. There we go. So really what we did here to answer this question is we assumed that the thing that we were trying to show wasn't true. So we assumed here that there were two or more obtuse angles in our triangle. And then we showed that that led to something which was nonsense. It just contradicted something that we already knew. So therefore, it must have meant that that thing that we assumed was true, that there were two or more obtuse angles in our triangle, was nonsense. And so therefore, our conclusion was our triangle cannot have more than one obtuse internal angle. And that kind of logical argument is often referred to in mathematics as a proof by contradiction. And this is what this section of the chapter is all about. Let's just have a look at those details again on the screen. The first thing we need to do is we start by assuming that the opposite of the statement that we're trying to prove is true. Technical word for the opposite here is negation. Then we show that the consequences of that assumption are impossible. They lead to some kind of contradiction, something which is nonsense, something which can't possibly be true. So our only logical conclusion is that the assumption that we made must be incorrect and our original statement must be true. So let's have a look at a more formal example now. I've left the method of how we do proofs by contradiction on the screen there, but you'll see there's an example there that we're going to prove that there is no largest integer, and we're going to use a proof by contradiction method to do this. So here's what I might write down. The first thing I'm going to do is I'm going to start by assuming the negation of the statement. So what's the negation of the statement? Well, the statement says there's no largest integer, so we're going to assume that there is a largest integer. Assume that there is a largest integer. And I'm going to give it a name. Let's call it n. Okay. So then we need to show that this leads to some kind of contradiction. The consequences of this assumption can't be true. They lead to some nonsense. So how are we going to do that here? Well, let's consider the number n plus 1. Now n plus 1 is an integer. Also, n plus 1 is greater or larger than n. There's our contradiction, of course. We've said that n is the largest integer. But this can't be true then, can it? n plus 1 can't be larger than the largest integer, but hold on, it is, and it's an integer. Therefore, we've got ourselves a contradiction. What does this mean? It means that our initial assumption here, that there is a largest integer, that can't be true. And therefore, we've proved what we want to prove, that there is no largest integer. Make sense? Hope so. Let's see how you get on with having a go at one yourself. please have a look at the one that's now on the screen. I'm going to leave the method up there for you to refer to as well, and just see if you can come up with a nice formal rigorous mathematical argument to answer the question on the screen now. Okay, how did you get on here? Well, let's see if we can have a look at this one together. So this one's about rational numbers. You probably know what rational numbers are, but there's a definition there for you if we don't. And we've been asked to prove by contradiction there's no smallest positive, I should say, no smallest positive rational number. So what's our method? First of all, we start by assuming that the opposite or the negation of the statements that we're trying to prove is true. So what's the opposite of this one? No smallest positive rational number. Well, assume for our contradiction that there is a smallest possible positive rational number. Smallest positive rational number. It takes a while to write these things sometimes. Okay, and because it's rational, we can write it in our form a over b. So let's call it a over b. Now, where are we going to find our contradiction here? Well, if we can find a smaller positive rational number than a over b, then we're done. And maybe we could just consider a over 2b, which is, of course, a half of a over b. And there is our contradiction. We assumed that there was a smallest positive rational number here. We assumed that that number was a over b, but then we found a smaller number. There's our contradiction. So our only sensible logical conclusion must be that the assumption that we made here is incorrect and there is no smallest positive rational number. Okay, hopefully it's all making sense and you're understanding the logic of how a proof by contradiction works. Just before we wrap up this video, I want to talk a little bit about finding the negation of some of these statements that we try to prove with proofs by contradiction, because one or two of them can be a little bit tricky. I've got a question on the screen here, which is simply just to write down the negation or find the negation of the statement all British men have brown hair. I've given you three options. Pause the video, have a think about it and restart when you're ready. Okay, so what do you think? A, B or C? Well, I'm going to tell you that the correct answer here is C. At least one British man does not have brown hair. The reason why it's not B is that all British women have brown hair. Well, that doesn't tell us anything about the British men. So, that doesn't really contradict, or it's not the negation or the opposite of the statement which we've been told at the start there. But you maybe think, some of you I think may have used part A there and written down the answer A. No British men have brown hair. Well, the reason why that's not the correct answer here is because, well, if some British men have brown hair, that's still contradicting. It's still saying that our original statement, all British men have brown hair, is wrong. So one thing which is really, really important to recognise when you're trying to find the negation of a statement is that the word all does not become none in our negation statement. The word all here turns into at least one doesn't. Hopefully that makes sense. So in our example here, we're not saying that the opposite of all British men have brown hair is no British men have brown hair. We're saying that the opposite is at least one British man doesn't have brown hair. Here's another situation which people often get confused about. Have a think about the one that's on the screen now. Pause the video and restart when you think you've got your answer. Okay, I'm just going to tell you the answer of this one now. Hopefully you've had time to think about it. The correct answer here is statement B. If it is raining, then there are no clouds in the sky. The reason why A or C are not correct here is because we have that condition here, if it is raining. That's given to us. We're not saying anything about whether that's true or not. We're told that is definitely true. So the opposite, or the negation of our statement, still has that bit true. It's just the other bit, the condition, the consequence, if you like, which has to change. So so when we have an if kind of if-then statement, so let's say if x then y, then the negation of that would be if x then not y, speaking more generally. I hope that makes sense. You might need to think about that a little bit to make sure that you understand why those are the correct negations. Now, to finish off this video, once you're happy and you think you've got the idea, let's try and piece it all together. There's a final question from this video for you to have a go at on the screen now. Pause the video again, write down your answer, try and write as formal and rigorous a proof as you can, and I'll restart the video very shortly. Okay, how did you get on? I've already started my answer here, so you can check and see whether your negation looked anything like mine. What I wrote down from the negation was that there exists an odd number n such that n squared is even. Notice I've not said that all odd numbers n have n squared is even, because that's not the negation of the statement. And notice I've not said that n squared is odd either, because again that's not the negation of the statement. The condition if n squared is an even number is going to stick with us, and then we're not saying that that all odd numbers would have n squared even, just that there's one of them. So there's our negated statement. Now let's see if we can come up with the proof. So because we're assuming this is true, so we're going to assume that that statement there is true, we can look at that number n. So n, because it's an odd number, we can write it as 2 times an integer plus 1, and then we can consider what happens when we square that. So we need to get an even number as our answer. So let's see what happens. So let's take that number, we'll square it. Now if I square that, we end up with 4k squared plus 4k plus 1. And of course, if I want to consider whether that's an even number, well then I need to think about, can I multiply it, or can I write it as a multiple of 2? Well, if I take 2 out as a factor from the first 2 terms here, we end up with 2 times 2k squared plus 2k plus 1. Now that plus 1 there, oops, there you go, hopefully you can see what I've done there. That plus 1 there is telling us that we must have an odd number. So we have our contradiction. And the assumption that we made up here, that there exists an odd number n such that n squared is even, that assumption cannot be true, because otherwise we wouldn't have ended up with this contradiction here. And we've reached the end of the video here, for the end of this section. It's really, really important that you do think hard about these ideas. Make sure that you follow what's going on with the logic of it. There are 2 standard proofs by contradiction which A-level examiners will expect you to be very familiar with. They're given to you in the textbook, examples 3 and 4. So please do look at those. Please do work through them and make sure you understand every step of the process. Once you've done that, then you might want to practice some of the questions in exercise 1A, which is on pages 4 and 5 of the textbook. And that's the end of this video.